Look at this application problem 3.2. This one's a really good problem for understanding the connection between an original function and a derivative, and I'd really like you to get the grasp of this problem. So in this one, it says we have a capacitor. A capacitor is a device with an electrical circuit that stores charge. In one particular circuit, the charge on the capacitor Q varies in time as shown in the figure. And what I've done on my graphing screen is I've tried to take the figure that was given and looked at it a bit closer, so I drew it. Now, to answer their questions, I needed to understand the graph of Q of t. So Q of t, notice here to begin with, it looks like it asymptotically approaches the y-axis. Well, at that point, as t approaches 0, the slope of it is really great. Now, there is no way to calculate what these slopes are without knowing an equation for Q. So everything that you see in red, that's my estimations of what it looks like the slope could be. So as I start off, as t goes towards 0, I can see that the slope of this function is going to get steeper and steeper and steeper. At the point where I chose to estimate the slope, I could say, well, that's a slope of approximately like y equals 10t. The y unit's going up 10 times as fast as the x unit's moving to the right. Now, that may not be accurate. It doesn't have to be. But what I do need to see is that as the horizontal variable increases, the slope is going to continually decrease. Notice it's less steep here than it is here. At the other point I chose right here, I said, well, that looks like a slope of approximately 2. And then as I kept going, that slope here, clearly the line is not increasing here as fast as it is here. I said this was a slope of 2. This was a slope of 1/2. As I keep on going on out, it's approaching a horizontal asymptote, which lets you know, hey, that it's going to continue to rise more and more and more slowly. It's going to start to level off as the y values approach that asymptote. I had that it was still going up at a rate of about a slope of about 1/4, so 1 y unit per 4 x units at about the time it reached 30. And that may be a little bit greater than what it actually is. It may be more flat than that at that point. But now, in order to graph an approximate derivative, we need to make the connection between the slope of the original function and the y value of the derivative. That's what I tried to explain right here. The estimated slope of the original function Q of t gives the estimated y values of its derivative Q prime of t. So whenever they're asking me to sketch a rough graph of the derivative, I can say, okay, I know that the derivative starts off positive. Why? Well, because this function starts off increasing. This function has a positive slope. Its derivative has a positive y value. The greater this function has a positive slope, the greater the y value is over here. So where I estimated the slope was 10, I took that x value and created a y value of 10 over here on the derivative. When I estimated that the slope was 2, right before x equals 10, I put a y value of 2 on the graph of its derivative. On over closer to about 20, I said the slope was slowing down to a rate of about 1 y unit per 2 x units at that point, a slope of 1/2. So I put the y value of 1/2 on the derivative function above 20. And then at 30, when I had the slope is 1/4 here, I have a y value of 1/4 on this. What we can see is that clearly the derivative is going to be a function that has a horizontal asymptote of 0. Now that needs to make sense to you because we can say the slope of this function is going to eventually approach 0 as the y value gets closer and closer and closer to that horizontal asymptote. Well, if the slope of the original function is approaching 0, then the y value of its derivative is approaching 0. Now, we would say that the original function is always increasing. We would say that the derivative is always positive because the derivative is, the y values of the derivative is the rate of change of the original function. So since this is always positive, the derivative is always increasing, but because its rate of increase is continually decreasing, that's why the derivative is going down. It stays positive because the original function is always increasing, but because the original function is increasing at a slower and slower rate, that's why my derivative here is getting more and more, or I should say a lower and lower y value. It's approaching an x-intercept of 0 in this problem. Now, to more specifically answer the questions, it says, at what time is the magnitude of the rate of change, the rate of change of the charge Q prime the greatest? We said, well, okay, when is the greatest y value of Q prime? And just like we can see that the original function asymptotically approaches the y-axis, well, as it does that, the steepness or the slope of that function gets greater and greater and greater. So I can say, well, okay, the greatest y value for Q prime is going to be when t is 0. Now that's assuming that t is 0 is undefined. As t gets closer and closer to 0, its rate of change for Q prime is going to be the greatest. And then it says, and 0 would be included because the next one it says for t greater than 0. So the answer to A is 0. The answer to B says, is Q prime positive or negative for t greater than 0? And you say, well, we know it's positive. Anytime the original function is increasing, its derivative has to be positive. And that's what this is saying, that the derivative is positive since Q of t is always increasing. And then part C, is Q prime an increasing or decreasing function of time? Or could it be neither increasing nor decreasing? Well, it's going to be decreasing. And again, the reason that Q prime is decreasing is because the slopes of my original function are decreasing. It's always positive because the slopes of my original function are always positive, but because the slopes are continually getting less and less and less, then the derivative is continually getting less and less and less on the y values as the time increasing. So we'd say Q prime of t is a decreasing function. And again, that's because since Q of t increases at a slower and slower rate. The slopes stay positive, but they get less positive. So the y values of the derivative stay positive, but they get less positive. All right, hopefully this helped make sense out of this problem.